Hi, I'm Mark Hamilton, and I'm a PhD student at MIT and a software engineer at Microsoft. Today, I want to share with you our application MosAIc, which aims to find hidden artistic connections across culture using a technique that we call conditional image retrieval. This work was inspired by a trip to the Rijksmuseum in Amsterdam. Here, there is an exhibit called Rembrandt and Velasquez, which sought to take two great masters of painting who never met each other and lived thousands of miles apart, and put their works side by side in dialogue. On the left, we have an example of the martyrdom of Saint Serapion, who has his arms outstretched in a defensive pose, protecting us from our sins. And on the right, we have the threatened swan, who, again, has a very similar pose with wings outstretched, protecting her nest from an unforeseen adversary. And so, in this particular example, these two works share a clear visual similarity, but it underscores a much deeper semantic similarity as well. These works are kind of trying to say the same thing. So we thought, what if we can make an algorithm that can find these pairs of works and try to generalize this not just between Rembrandt and Velasquez, but between any two subsets of a large collection of art. To do this, we used a variation on image retrieval. Basic idea is that you can imagine a reverse image search engine on a collection of art. You can feed in an image and ask for the closest image in the collection. So you might get something like this, where it's very visually and both semantically similar. But this isn't quite going to get you what you want. This isn't going to get you a perfect pair between Rembrandt and Velasquez. For that, we'll need to modify our query by a condition. We want the closest image in the collection by a collaborator of Rembrandt. And that constrains the search to only find the images that span this gap between Rembrandt and Velasquez. This is what we use to kind of power an algorithm that can find these matches across the collection. This approach that we call conditional image retrieval is able to take a single starting image and find its closest matches across any subset of the collection. In particular, you can find matches by media, so you can take, say, the double-faced banyan on the left and find the closest musical instrument, something that's kind of an exotic query that you couldn't imagine doing yourself. You can also use it to find works that span very disparate cultures, so you can take something that's Dutch and find the closest Nigerian artwork. And what these particular works are not just kind of visually striking and exactly sort of what you expect, they also underlie some art historical trends and shared semantic meaning across these gaps. Here's one particular example how this algorithm, which really looks for shared visual structure, is also able to find shared semantic structure. Here we have a model paddling boat from about 2000 BC, so a really long time ago in the Middle Kingdom of Egypt. Finding its closest match in the Chinese collection gives almost an identically structured wooden raft from the late 18th century. And these works of art are not just strikingly similar, they also are used in a very similar purpose. For instance, the model paddling boat on the left is used as a funerary offering in Egypt, so it's designed to kind of guide you into the afterlife. On the right, the immortal raft is designed to give you safe passage to the immortals, or the gods, kind of serving a similar role. So it's really interesting that even though these things are visually similar, it's starting to pick up on something that's shared between the two, even though these works of art are separated by 3,000 years. What we're particularly excited about is that this method can find art historical tropes that span the millennia. Here we start with a painted panel of Tatiasid in Egypt. You can see that it's framed in an arch and is symmetrical. We move on to the Renaissance for a wood and gesso painting of David in 1400. And again, very similar framed arch, and instead of a headpiece, now you have a halo. We move forward to 17th to 18th century China, and we look at a woven silk tapestry of the Bodhisattva. And again, you see this same kind of arch framing, very symmetrical construction, And this halo and crown is again replaced with a similar halo, but in a very different style. And finally, we see the quote-unquote secular version of this in the American mythos. What's kind of the American figure of reverence but George Washington. And instead of a crown or a halo, he's now framed in a portrait hole. And again, the same symmetry throughout. So what this kind of shows is that over the course of 3 millennia, the kind of composition of works for figures of reverence shares a lot of the similar structure. And these are just some of the examples of some of the art historical trends that you can find by exploring the collection with this particular kind of image query. To help you and others explore this collection for yourselves, we have created an interactive website that allows you to use this technique on the combined art collections of the Metropolitan Museum of Art in New York and the Rijksmuseum in Amsterdam. You can go right now to aka.ms/MosAIc to check it out for yourself. Here, we'll try it out. Here's the MosAIc application. To get started, you can pick any image from a list of really good ones that we've picked out, and you can start from this image and look for its conditional matches across various different media or cultures. So here you'll find its closest match in the textile collection, but you can also scroll down and check out other textiles or look at its closest matches across cultures. So here's a really close match across in the Chinese collection. You can choose from a wide variety of different cultures to start from to find things that are close matches. And you also have a wide choice of media. So let's say if I want to find the closest work of art in glassware, you can select glass here. And you'll see this is sort of the closest image in visual and semantically. And let's say now I'm interested in this new plate. I can use this as a new starting point for my conditional image retrieval. So I can use the match as the query right here. So this now allows me to find works that are related to this particular object. So I'd come in and find the closest ceramic work or the closest cross culture here. And let's say I have a particular image that I'm looking for. I can also come down here and do a full freeform search to pull up any image in the combined Metropolitan Museum of Art and Rijksmuseum collections. Let's say I want to look for turkeys. It's getting close to Thanksgiving. You'll see that you can browse through the entire collection. Anything that has anything to do with turkeys will come up. And let's say you want to pick this one. You can click on it. This will pull you back to the main page here. And now you can kind of find new works across the different genres. So here we have one that's from the African collection. You can see that it's correctly identified the shape and the form of the rooster. And you can also kind of explore down here. So let's take a look, see if we can find a glass version of this turkey. And indeed we find this crazy covered figural dish from the American collection that's in the shape of a bird. And you can really have some fun and explore this in a fairly free-form manner. So you can find paintings of turkeys, and there's all sorts of different ways you can kind of take this one image on the left here and transform it into other media or culture on the right to try to find your own cultural connections between art. So now that you've seen the final product, let's take a look under the hood. The core of this approach is a deep image retrieval engine, and we use a fairly simple one. We take images, we featureize them with an intelligent deep network like ResNet 50, and these features, they're much denser representations of images, and distance in feature space much better corresponds to similarity. Here in feature space, we can just use fast k-nearest neighbor lookup to find the closest matches for a given image. But this is only part of the problem. Namely, this isn't the closest conditional match. What we want to find is the closest match, but restricted to a given subset of the collection. And for that, we'll need to think a little bit harder. This problem isn't quite as easy as it might seem on the surface, because let's say you have your manifold of featureized images and you're looking for the closest glassware to this particular dress here. The problem that might arise is that the glassware might be very visually distinct from the dresses. So if you were to just do nearest neighbor search, it would take you a long time before you got to any of the glassware. And this is kind of one of the issues, that just applying regular k-nearest neighbor search and then filtering after the fact really breaks down. It's no longer fast. It still requires basically a full scan of the data. So it's not really feasible for very, very large image collections. So our work really aimed to find a more efficient approach to be able to perform this problem. In order to make an efficient conditional k-nearest neighbor method, we need to think about what an efficient unconditional k-nearest neighbor looks like, or just a regular k-nearest neighbor tree. And so we're going to take a look at the ball tree. This is a fairly common algorithm, and the basic gist is that you don't want to search through the entire collection of points. You just want to narrow your search first to a small neighborhood of points. So the way you do that is you recursively split up your data and nest it inside of hyperspheres. Using things like the triangle inequality or the Cauchy-Schwarz inequality, you can prune away huge swaths of your data set, entire hyperspheres, and continue on recursively until you get down to a point where brute force search is efficient. You can just search through the things in the tree and find your closest point. So the idea is that you do this and you create a tree of balls, or a ball tree, that captures the topology of your data. Then when you have a query, you can prune these balls away and find a neighborhood that you can search through efficiently. But this isn't quite conditional yet. So the idea is, what if our points have a condition associated with them? Say an artist, or a media, or a culture. Here I've denoted these in colors. So the idea is that we want to not just search through the entire tree, but really only search through the tree that contains points that we care about, in this case, blue points. For that, we kind of want to prune away all the unnecessary nodes and leaves of the tree to just get the subtree that we're interested in, the subtree that contains blue points. And from there, we'll have a much easier time searching the tree. The way we do this efficiently is with an inverted index. What this particular structure is it's a map from our conditions, or our data set, into the subtrees of our larger unconditional tree. So here we have a map that takes us from the condition we care about to the set of parent or dominating nodes of all the different subtrees. So what we can do is, if we want to find the subtree associated with just the points from the yellow condition, we can query our inverted index and quickly get that. Now we know exactly which part of the tree we should be searching for, and we can forget about that whole other side of the tree, making the query much faster and much closer to real time. Now, we find that this approach is much better than a lot of others. In particular, query then filter really slows down, especially when the size of your subset is small. And another approach is that you can adaptively switch to brute force if you get a small enough subset that it makes sense to just filter and check manually. And again, this is kind of limited by the speed of brute force search, and doesn't really work with larger or medium subsets. So what we found is that this conditional tree pruning approach is really gets the best of both worlds. It gets you fast query time if you're not doing any pruning at all, and also fast query time if you're doing lots of pruning on the tree. So with this, we can now swap out in our original deep image retrieval the k-nearest neighbor method with the conditional k-nearest neighbor method. From there, we can solve our original problem. We want to get the closest images under a conditioning filter, like say that the medium is a painting and the medium is a ceramic. And this really allows us to find these pairs of images that straddle these two classes. So to tie everything together and understand how we actually built our application, we take all of the artwork and images and metadata from the Metropolitan Museum of Art and the Rijksmuseum. We pass them through a deep pre-trained ResNet 50 to get tight, pithy image features. We then use conditional image retrieval to find their closest neighbors in all of the different categories at the Met, all the different cultures and media. And finally, we take all of this data and we put this into Elasticsearch. And what this serves is a really fast, snappy backend that we can use to host a React front end to actually create that application that allows you to play with it in real time. So I got to give thanks to the fabulous Microsoft externs who really did bulk of the heavy lifting on that front end that you see. And so thank you, Stephanie, Mindrin, Ben, Felix, Darius, Maggie, Marina, and Johnny for all of your hard work in the winter internship. So if you're interested in learning more, you can take a look at 2 of our papers. Conditional image retrieval really has the bulk of the work. And to learn how we can efficiently orchestrate this and push this all into Elasticsearch, you can check out our paper, Large-Scale Intelligent Microservices. If you're interested in checking out the website, it will be up on aka.ms/MosAIc. We've made all of the code open source at Microsoft/Art. It's the GitHub repo. And finally, if you want to have any specific questions or want to get in touch, please feel free to drop me an email. Thank you very much, and enjoy the rest of your NeurIPs.